The 10th of December 2023, and it's about 11 o'clock at night. I'm soon going to turn in, and I've made two videos there which I'll upload in a while. I hope you enjoy my videos. I want to change the tack a bit, and hopefully around the Christmas I'll get away from politics altogether, if that's possible, and move into something more enlightening and something that people may enjoy. One of the hardest things is for me to figure out what people like, what people want, and I try to do that. And I don't want to be all typecast in the one political given out um, uh, uh, role. So this is science and nature. I'm just going to talk about science for a minute. Uh, I believe that science really is nature. Science is a fancy word really for nature, because all of science has always been about figuring out what tricks nature is up to and what nature is really about. Now, a lot of it is fully agreed and established. It's at the fringes, at the extremes, that scientists agree that don't fully know it all. And there's two parts of science. There's the big cosmos part, the galaxies, the universe, and there's the tiny atomic and subatomic part. And it runs the whole gauntlet right up the whole way. Excuse me. I've claimed that there's no such thing as an object. There's only a collection of atoms. Now, the thing about it is that they think that the universe came into existence about 13.4 billion years ago with what's known as the Big Bang. Now, no scientist asserts this 100%, and I like that about modern science. Neither Stephen Hawking or anybody else, but they say this is very likely what happened. And all the time, the various probes and telescopes keep giving us more information. And I was a bit skeptical about whether man landed on the moon or not, and I was skeptical as to the footage and the photographs that came back from there allegedly and all of that. So I don't really know, and I'll deal with that separately. But what I do know is that many countries have put up an awful lot of probes into space, and NASA in America have been to the forefront of that, and we can't deny that they have done some Trojan work. Now, after the Apollo missions and all that, there was the Voyager 1 and 2, launched about 1977, and they were fantastic probes. And then there were the various ones to the sun and to the planets and all of this. Now, the big thing then was the Hubble Space Telescope, which again, I believe, and I believed it because when they put it up first, there was an error. There was some type of misalignment of the reflective mirror. And that proved to me it was right, because if I'm reading a letter from somebody or a statement from somebody and it's written by hand and there's no mistake in it, I begin to suspect it. The fact that they made a mistake and got it fixed proved to me it was genuine. And then there was last year's the James Webb Telescope, and the camera parts for that were built in Waterford and Dublin by even people related to me, would you believe? And it is a fantastic bit of kit. It measures in the infrared spectrum. Now, what we can say about NASA, and indeed the European Space Agency, if they found something in their exploration of space which benefited them, or benefits their own country, like America, they wouldn't tell us. And they may not have tell us all, but they do tell the general stuff. They will tell us they discovered volcanoes on Io, the moon of Jupiter. A lot of that is correct. So it's not that they're telling us false stuff, it's that they will hold back on some of it. Now, these probes and telescopes and that, they did prove that what scientists themselves had considered to be true about the cosmos was reasonably true. And they've actually managed to photograph a black hole, and Einstein predicted that, and it makes perfect sense. And I have to admit that I can understand that stuff a lot. I can understand gravity and how it and all of this um, galaxies and all that stuff. Now, the only galaxy you can see with binoculars is the Andromeda galaxy. It's at an angle. It's sort of at an edge like that to you. You know, you can see just a bit of it. It's a great pity it's not flat onto us, but it's not. And apart from that, you cannot see the stars in any galaxy, including Andromeda. So when you look up at night and you see stars in the sky, you are seeing all the stars in the Milky Way area, in the arm of the Milky Way we are in our locality. And it's 100 light years across. There's 100 million. It's an awful big galaxy anyway. But you're only seeing the stars in your immediate vicinity. Okay, so it's like if you go to a town, you go to, we'll say, Thurles and Tipperary, and you see people walking around. Those people are only a representative sample of what you see in any town in Ireland, but it is unique to Thurles. Do you understand? You're just seeing your immediate vicinity. But these telescopes can see beyond and into far distant galaxies, and they can actually, in one case, they just selected a very dark area of the sky, a very tiny little area like that, a wee square, you see, and they shone at it, and it was loaded full with millions of galaxies. So what it does appear as what we think the size of the universe is, that it's actually 1,000 billion times bigger. That seems to be the case. Now, there's a big debate on does it have an edge and all of that. Scientists are constantly shocked by the sheer number of stars and the sheer size of the universe that they can observe, and we can assume we're only seeing a tiny portion of it. On the other scale, as you go back down, they tell us there was a big bang. That's not fully confirmed, but the theory was that the universe expands, contracts into a little singularity, expands and contracts. And we're in one of those. And as Hubble was able to check the spectrum, the Doppler effect of the light coming from distant objects, he was able to say that the universe is expanding. But the other thing is, there is no sign that it will do otherwise. There is no real evidence that it's going to stop and fall back in on itself. What actually appears to be happening is that the universe will expand forever until eventually the Earth will be gone, but anything that's around will be more or less on its own. That the distance between the various parts of and various galaxies will grow and grow, so that will grow and grow into oblivion. Now, the other thing that I can be a wee bit more sure about is what happened after this event, whatever it was, so there was Big Bang or whatever. What happened after the event was that there was a huge expansion. Whatever condition existed, there was huge pressure and temperature, and the natural way for this to behave, and it was all energy, because don't forget, under Einstein, energy E equals mc squared. It tried to expand and cool down, and it did. And in the beginning, the laws of physics didn't apply, but as it cooled down and settled, the laws of physics arrived back on the scene. And one of the first laws of physics is that nature can count. And it seemed from the beginning that it counted in binary, in two. So if you take a magnet, which is the basis of electricity, it has a north and a south pole. And if you split the magnet down the middle, or down anywhere, split it down here, each side will have a north and south pole. You can't have a south pole on both ends. a magnet cannot be unipolar. It can only be bipolar. It can only have north and south pole. And that applies to the very earth we live on. Now, the metal in the earth creates a magnet. The earth is a giant magnet, and the pole that's up towards the North Pole is actually the South Pole, right? It has a minus sign, some people say, right? But if you have a magnet with the North Pole, which is a compass, the North Pole is attracted to the South Pole, so they call this the North Pole. So this will attract the North Pole, and this will attract here, this will attract the opposite. So opposites attract, do you understand? So this binary nature, and funny enough, even in the design of living creatures like ourselves, we have 2 eyes, we have 2 ears, 2 arms, 2 legs. It's funny that the 2 applies an awful lot in nature. Nearly every animal I ever heard of has 2 ears and 2 eyes, and so that seems to be one of the things about nature. But just to finish off, when it cooled down, the next thing was there was the development from the cool radiation was the proton, and the proton is the particle of the atom. And then in basic, very elementary hydrogen, you have a neutron. And there's a neutron. Now, the neutron, the proton has a positive charge, and the neutron has a negative charge. Has no charge. It's neutral. Okay, sorry about that. Now, so I'm going to draw the basic hydrogen, the first matter, the first gas that ever appeared. So you see the green, that's the proton, and it has a plus to give it. I have a bit of an issue with that, but it has, we'd say, a north charge. The neutron has 0 charge. It has none at all. And so there was a bit of tension in that. Well, then above that, as it settled down into hydrogen proper, you have another device which came in on the act, and that's the electron. And the electron is a tiny dot, and it's only a tiny part, and that's the electron. So the proton and neutron revolve around each other using the weak and the strong magnetic force and the weak and the strong nuclear force, and so the electron does the same. It revolves around it. Now, you wouldn't have an electron if you didn't have the particles spinning around each other. You couldn't have it. The idea that they can be stopped and you can look at them is nonsense. And they can use electron microscopes to take a tiny sliver of gold and actually see the atoms in it. And if they're online, you can get them. So the atom comprises the proton, the neutron, and the electron, and they're going around each other, driven by an unbelievable powerful force. And if they were allowed, they'd keep going round till it had become so unstable with the centrifugal force that they'd be inclined to fly out. And to work that, nature has a speed limit in nature, and that's known as the speed of light, SOL. Now, it's not true that light is the measure of the speed of light. Light is the one thing that can travel in a vacuum without any hindrance and reaches a speed from the very start and sticks at that speed all the way up. And if it could, it'd accelerate further if there was any force behind it, but it can't. It's limited to the speed of light. But that speed of light limit also applies to the circularization of the orbitals. These parts go around in orbitals. They're a bit different to the orbit. And because they're going around at such an incredibly high speed, when you get a group of them together, they're a natural solid. So if you catch a metal lead ball in your hand and it feels to be a solid, really the part that's in touch with your hand and your hand as well has electrons flying around it. And if you put electricity up to that, you can actually see the sparks flying from the electrons in it. Okay, so that's what it's like. An atom is like a green-grey blob. These are going around at an unbelievable speed. And if you could send them through a fibre optic cable and you wound a wire around the Earth, would say you wound it around 10 times, and you put a beam of light, a pulse of light in any point on the globe, it would go round eight times and a little more. 8 times in 1 second. That's how fast it is. And so that is where the speed of light comes in. It's a bit of a mistake to think that it's the light flying out from the atom. The light is sourced in the atom. As you disrupt the orbitals, they do it in discrete steps. They give out electromagnetic radiation, and that has a spectrum, and included in that is visible light, and included in that is radio waves. You see, so the electron, the proton, the neutron are flying around. Now the electron has a negative charge. I don't like the idea negative, it has a sound. It's opposite to the proton. And the proton and electron balance each other out. And if you put in an electric charge or energy by way of heat, you disrupt the speed at which the orbitals go around. Now there are other things such as quarks and all of that. Now one thing that can't change is the proton, and the neutron can, and you get isotopes and you get ions and all of that. The electron and the neutron can change a bit, but the proton can't. And the proton, when those original hydrogen atoms were fired out into space and come together with gravity, they formed into stars. And as those stars died and as those stars collapsed, they went through an unbelievable pressure wave, and up to iron 26 atomic number were created in the dying stars. And in this case of very big stars like supernovae, when they collapsed in each other, and they gave them like a hammer blow, like that. A huge impetus, like a hammer hit or a hatchet hitting a block of wood. It gave it a more power than could be got by direct pressure, and that formed the elements above 26, from 27 right up to about 100 roughly, including uranium and all of those, gold and all of those heavy elements. And so whereas the hydrogen would be like this, a different atom, a bigger atom, might have more protons, and it might have more neutrons, and it might have more electrons all around. Do you understand? So we'll say there's different type of ones. Lithium is 3, I think, is 3. I know iron is 26, and gold is 79, is it? I think it is, and all that. But and silver is something like 49. But whatever it is, anyway, these all have different properties, and that's how our modern world is built. As I say there's no such thing as an object. There's just a collection of atoms. But it's very important to understand that the proton does not change. It proves nature counts. So depending on the number of protons that were squeezed into the atom together in that dying star, conditions that could really not be produced on Earth at all, in extreme conditions, that sets out the chemical composition of the various elements that there are, including copper, carbon, oxygen, very important one, and all of those. The basic one is hydrogen, and as you press them together, you make all of these other ones. And there are slight differences in the electron, slight differences in the neutron, but the proton number is exact. It's either 36 or 37 or 35. There's no 36.2. There's no 78.6. It's either one or the other. There is no element that will run between two metals, that will exist between two metals. It's either gold or it's something else adjoining it, and you'll get the periodic table there to show you. There's a certain amount of them metals, a certain amount of them are not, are other things. And we are primarily made of hydrogen and oxygen in the form of water, and there's a good deal of carbon in our bodies as well. So with that, folks, I'll let you go. I think that's the basic point. That's the natural world out there. And then from all of these atoms, certain molecules can be made. They can cling together, and you can get a compound of two particular atoms. And then it gets really interesting. You're then into chemistry, and you're into the whole world that we see around us, which mostly uses both elements on their own and compounds of a number of two or more elements. We'll see you back for something else. That's maybe not that interesting. It will be interesting to see, do I get many likes for that? But that is the basics of the world around us. And it is a humble thing to really realize that if you get the most powerful telescope and put it up in space and look out into space so far that the object you're seeing is billions of years old. It's gone now. I mean, we have a star called Betelgeuse in our own galaxy arm. It's up in Orion Nebula, and it could have burst into a supernova for 400 years ago, 200 years ago, whatever. It could have burst last January. We won't see it till the light reaches us. So you're really looking back in time. But it's sobering to realize that as they look out, no matter what they see, up to now, and I think this will never be changed, they're seeing atoms, they're seeing a collection of atoms, and they give off a colour. So you can know sodium by its yellow colour. You can know potassium by it has a kind of a pucey beetroot type of colour. And you can know all the other elements by the colour. In the case of the sun, it converts hydrogen into helium, and that's why if you burn hydrogen on a sunny day, you won't see the flame, because that's what the sun is doing as well. So the light from the sun is actually the same light as you burn hydrogen into helium here on Earth, and it can be done easily on that. I've done it on a video. So that's my little bit of a science talk for today. As I say, I'll be very interested to see, does anyone give a damn bit of difference? But it might be, it just might be. Good luck, we'll see you back. Thank you.